Hello, algebraites. We're going to be continuing on 2-4 exponential functions, part 2. So our goal is to understand and use exponential and decay functions. So previously, we talked about exponential growth and decay, and A was the initial value or initial population, and B is my growth rate. X is usually, if it were a population, X would be the number of years after a certain event, and f of x would be your population at that point. But it doesn't have to be population, it could be other things as well. So here was a population example, and then we talked about money growing in CDs. So now let's be specific and talk about exponential growth graphs. What do they look like? Well, exponential growth graphs, they are going to increase. So this growth occurs when? Well, specifically when b is greater than 1. So let me give you an example of that, right? So f of x is equal to, just making something up, 3,000 times, and here's my b, 1.04 to the x power. So here we have an initial population of 3,000 and a 4% growth. In other words, 104% happens every year. So that's called a 4% growth. Now, this is not going to be the graph of that function, but I'm just going to show you, generally speaking, what happens with exponential growth. So it's going to go like this. Whoop, let's try that again. Goes up forever like this, up and out forever. And this one down here is going to almost touch but never touch the x-axis. So it starts really small, goes up here, but if we're talking population, usually year 0 is right here, the initial population. All right, so let's think the other way now. Exponential decay function, it graphs as a decrease. It graphs as a decrease. So let's look at what that might look like. So here we have our graph, and it's going to come down like this and decrease in such a way that it almost touches 0, but doesn't. So an example of this would be something like an isotope that's decaying, because we start with an initial value and it has a half-life, and every week it decays. But even years later, you still see a little bit of that isotope. It's still there just a bit. All right, so this would be called the decay function. And when does that occur? Well, that occurs when our b is less than 1, except it also has to be greater than 0. So it does have to be positive. So I'm just going to make something up here. F of x is equal to, we have start off with 37 milligrams of something, and we have it gets cut in half every unit here. So there we go. This would be an example of decay. All right, on the next page here, I would like you to pause and watch the other video, and so that you can do this by yourself. You're going to be using your handy-dandy TI-84 in order to get the exponential function, or the exponential reg. We're going to use the exp reg, and you're going to enter 2 points into L1 and L2. So pause and do that. And now we're back. And I've done all these, and you may have noticed one issue. When you were doing F, you probably got an error, and it said domain error or something like that. And here's why. Because when we use these points, and let me show you those points, this point here is 0, -20, and then the other point is 2, -2. And of course, you put this one into L1 and this one into L2. What happens is the calculator doesn't know how to manage these zeros. So here's what we should do instead. What we're going to do is pretend that it's actually the exact same function, but flipped, okay? So here is my 0, +20, and here is my 2, +2. So this is 2, 2 there. So with that in mind, what we do is calculate it, and then we just toss a negative in the front. If you remember from your transformations that if we put a negative outside of the function component, what it does is it flips the flips the graph upside down. So that's what this guy is going to do here. So that's where I got that. So let's look at some common features. Now, I would like you to do this, of course, pause and think about this without me, and then come back and verify some things. So let's compare and contrast. So notice all of these ones here, A, C, and E, what are they doing? They're all increasing. They're all increasing right there. And these ones are all decreasing and decreasing. And wait, what's this one doing? Actually, this one is doing an increase of some part, but it doesn't increase to infinity up here. It increases closer and closer to the x. So what is something that is common about some of these is it looks like that A, C, E, and F are increasing, and then B and D are decreasing. But what's something common in all of them? Well, let's see here. Notice that all of them never touch the x-axis. Never touch the x-axis. And we call that an asymptote. All right, so an asymptote is not part of the function or not part of the graph, but it is a thing or a limit. It's a limit that the graph approaches. Now, we often will draw the asymptote onto the coordinate plane, and let me spell that right, approaches, in order for us to see what it is approaching, but this is actually not part of the graph. The blue, only this blue is my graph. Everything else is just helper information, right? The coordinate plane, the numbers here are just helper information, background information, as is this. This is background, because this blue curve, which is my graph, is approaching the axis but never touching it. Something else that's common, and it's hard to see without looking at these, but notice this 5 and then that 5 there. This has an 8 and that has an 8 here. This has a 1 that's hidden, and this one has a 1 right there on the Y. This one has an 8 also, and D, and we don't see that 8, so it probably is there. 6, and then this one is probably a 6 right here, and then negative 20, we do see that. So something that's common is that inside the function itself, we see where the y-intercept is. We see the y-intercept. Y-intercept is the a value. And again, let's be specific what we mean by that. The a value is a times b to the x power. So this right here is my initial population as we did before, and that is going to also be my initial starting point, my y-intercept. All right. You could also look at some other commonalities about the nature of the base here. This is a positive 2, this is a positive 3, this is a positive 3, and let's see what's happening with them. A, C, and E. A, C, and E. Oh, look, they're all going in the upward direction. This is positive 1/4, but it's smaller than 1, smaller than 1, and smaller than 1. And what they are all doing is approaching as x gets larger, it is approaching the x-axis, approaching the x-axis, approaching the x-axis. All right, so let's compare and contrast to an example number 3 here. For each function characteristic, compare and contrast the linear function, f of x is 2x plus 8, that's this guy here, with the exponential function, g of x is 8 times 4 to the x power. Okay, so first off, our immediate look is, wow, they're nothing alike. This one's straight, this one bends. Not only does it bend, but it bends radically. It feels like 90 degrees. It's not, but it feels like it. So let's start breaking some things down here. Domain. What is domain? Remember, domain is the values of x that I'm allowed to put in. Notice that I have y values represented in all of those, which means that my domain is going to be all real numbers. So A, both of the domains are all real numbers. And we can use that symbol there for real numbers. But what about the ranges? Okay, are the ranges the same? Well, notice this. This values of y here go down forever. We have them all represented there. But this one doesn't. It only has positive values. In fact, notice it never gets to 0. Right here, it looks like it. As we zoom in, it looks like it, but that's just the nature of printing and the fact that we can't zoom in even further to see that this blue curve never actually touches the x-axis. So the range on this one would be the positive numbers. So y is greater than, but not including 0. And the range on this one over here is going to be also all real numbers. Okay, so what's the same? They both have the same domain. What's different is the ranges, the output. This is only positive numbers, and this one here is all real numbers. All right, let's look at the x-intercept and the y-intercept. So start with the y-intercept. Y-intercept is here, and let's see. The y-intercept right there is 8, y también aquí, also 8. And do notice here, we have an 8 right there, and we have an 8 right there, a positive 8. So that's where we can actually find those. So part B, same y-intercept. Okay, now what's different? Over here, the x-intercept, this x-intercept is clearly going to be -4, but this one here has no x-intercept because the curve approaches the x-axis but never gets there. So no x-intercept. Next, an asymptote. Yep, this one does have an asymptote, and this one doesn't. It goes on forever in down to the left and down, and this one goes up and right forever. So in terms of asymptote, no asymptote. And this one has the asymptote of y equals, y equals 0. So the line, this line is called y equals 0. All right, increasing or decreasing. Now, it turns out both of these here are increasing. Try that again. Increasing. What do I mean by that? Increasing means as I read from left to right, as I read, what does the blue curve do? And this one says, oh, as I'm reading it, it goes up, 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 up. As I'm reading, it goes up, 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 up. So that's what we call increasing. So let's summarize and bring things together about our friend exponential functions. Now let's clarify here, of course, what we mean. F of x is equal to a times b to the x power. So the domain of this, of all of these, no matter what happens with a and b, the domain is going to be all real numbers. And I do want to point out to you, you have to have some restrictions there because a can't be 0. A is not 0. And like we mentioned earlier, the b has to be positive. So b has to be greater than 0. Okay, now let's conceptualize this and see what happens. If a is greater than 0, what is greater than 0? Oh, so a, in this case, a is positive and a is negative for this one. So let's think here. If a is positive, we have two scenarios. If a is positive, we either get this situation like this, or we get this situation like this. If a is negative, it flips things upside down. So we get this little guy here, or we get this guy like that. And I apologize, that's not a parabola, so flat lines almost. All right, so then the range is positive numbers. And here the range is negative numbers. All right, the graph contains the point. Dun, 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 dun. It always contains the point, kind of like the b on y equals mx plus b. B tells you where to begin. Well, that's kind of what's happening here, but this point, we're not using the letter B, we're using the letter A. So again, point that out. Here's my 0A, and here's my 0A. No matter what, it's going to pass through that right there. And A is this guy right here, or this guy right here, the initial amount, or initial population in population growth equations. All right, always the x-axis is the asymptote. Another name for that, or not name for that, but a function is y equals 0. Y equals 0. For positive values of a, if b is greater than 0, greater than b, So positive values up here, like this. And then we have if b is greater than 1. If b is greater than 1, then this happens right here. That means it is going to grow. So the function is increasing. All right. So, in fact, we could actually break this down a bit right here and see some things, right? So this is b is greater than 1, and this one here is a is greater than 0, and a is less than 0. So over here, what happens with b is less than 1, but it's also greater than 0 there. If b is between 0 and 1, then the function is decreasing. And again, that's what this looks like here. It goes down, and again, it's decaying. It's going down, but never going away completely, like radioactive material. And for negative values of a, here, things flip around. So the situation is reversed. All right, that concludes our 2-4 exponential functions work. Have a great day.